Hello, everybody. This is Bert Dixon here to present on the topic of compound interest. This is section 13.4 in your Algebra 2 book and starts on page 681. So go ahead and open your book up to page 681. And we'll start with the example that's down near the bottom of the page. Before we introduce compound interest, we're going to do a quick example of simple interest to make sure you understand how interest works when it's not compounded. And so in simple interest, the interest you earn each year is not reinvested into your account. So for example, if you invest $1,000 in a simple interest account that earns 5% per year, 5% of $1,000 is $50. So you'd earn $50 of interest in the first year. Your investment at the end of the year is still $1,000 because you're not reinvesting the interest. And then the next year, the same thing would happen. You'd start with $1,000, you would earn $50 in interest, you'd still have $1,000 at the end of the year. And then the same thing during the third and fourth years. And so by the end of the 4 years, you've earned a total of $200 in interest, and your original investment of $1,000 is still there, and so now you have a total of $1,200. So that's simple interest. That's without reinvesting your interest and compounding it as time goes on. So then go ahead and flip forward to the next page. We're going to change this example from your book slightly just to compare it to the $1,000 investment that we made in the first example. So this time we're going to again invest $1,000, so you can cross off the numbers that are in your book and replace them all with $1,000. And so during the first time period, during the first year, we'd earn $50 in interest, and then we're going to add that into the account. And so now, by the end of the year, we have $1,050 in the account earning interest. And so then, at the start of the next year, that's the amount that we're going to start with. So we start with $1,050, and we multiply by 5%, so 1,050 times 0.05. 1,050 times 0.05 is $52.50. And so notice in the second year we earned a couple more dollars, $2.50 more than we did the previous year because we have more money now earning interest. And so now we're going to take our starting investment for that year and add on our interest. So by the end of the year, now we have $1,102.50. And then that process will repeat. So I'm going to let you go ahead and press pause on the player and see if you can fill in these next two rows and see how much money you end up with in the end. Okay, so now you can go ahead and compare your results with what I got here. And so I came out with a total of $1,215.51 by the end of the year. And so just to contrast the two examples, in the first example, we didn't reinvest our interest. We just took our lump sum interest at the end, and so we ended up with $1,200. But when we compound the interest at the end of each year, we earned an extra $15.51. And that may not seem like very much money to you, but if you're talking about a much larger investment, maybe $10,000 or $100,000 or $1 million or something like that, the compounding makes a significant difference. Also, we only compounded once per year. And what we're going to investigate a little bit later is what happens if we compound more often than that. If we compound every month or every quarter, which would be 4 times a year, or every day, which would be 365 times per year. So we'll go ahead and look at those different scenarios. Okay, and so when we do compound interest, when we're compounding annually, we're just going to use this equation, V equals principal. So the value of the account is the principal times 1 plus the interest rate to the t power. So for this example, we're investing $3,500. And the interest rate is 3%, so that's going to be 1 plus 0.03 raised to the t power. And we can simplify that and write 3,500 1.03 to the t power. And so if we want to see when that investment is going to reach a value of $10,000, okay, we invested 3,500. We want to know when it's going to eventually reach $10,000. What they did for this example is they graphed the horizontal line. This line would be, for example, y1 equals $10,000. And then y2 is this function, y2 equals 3,500 1.03 to the t. And then just like we did over the last couple days, we see where those two curves intersect. Okay, so we'll do one of those in just a minute. So just make sure you have that equation highlighted. That's what we use for compounding annually. So compounding annually, we use that equation. So if you go to the bottom of that page, go ahead and try problem number 3 in your groups. We're investing $1,000, 5.5%. We want to know how long it's going to take for the investment to double. Okay, what equation did you use for the account? Megan?
1,000 times 1.055
Yeah, T or X. So yes, the initial investment 1,000, 1 plus the interest rate is 1.055 raised to the t power, and then so we're going to graph that as y1. We can change that to an x to put it in our calculator, and then y2 we'll graph. If we want the investment to double, then we want it to be $2,000, and so then if you put that in the calculator, there's 1,000 times 1.055 to the x, and y2 is 2,000. So when you graph those, I chose a window of 0 to 20 because I thought it would probably happen within 20 years. And then the y values 0 to 3,000. That way you can see it grow from 1,000 up to 2,000. And then the graph looks like that. And so to find the intersection, second calc, option 5. And then first curve, that's it. Second curve, that's it. And then guess, you can move a little closer, but you don't really have to get that close. Press enter, and it gives you the intersection at 12.9 years. So about 12.9 years. Okay, any questions on that? Okay, so then what if we want to compound more than once per year? What if we want to compound every month or every quarter, which would be 4 times a year, or every day, which is what a lot of banks do. They compound every day. So they take your balance at the end of the day, figure out how much interest you earned during that day, add it into your account. And so we need to be able to change the frequency of how often we're compounding. And so this is the equation we would use for compounding more than once a year. So n is the number of compounds per year. So this is when we're compounding n times per year. T is still the number of years. So T for all these different equations, T is always in years. So that's a good thing to note. T is in years. Okay. And so using that equation for this example, We have $12,000. 2% compounded quarterly means 4 times per year, so n equals 4. And so then we would have the value of the account is the principal 1 plus the interest rate is 0.02, and we're dividing by 4, and then we raise to the 4t power. And in this case, it simplifies to 1.005 to the 4t power. Now, when you do this, when you divide these numbers to try to simplify it into an easier decimal, if that gives you a really long decimal, you're better off just leaving it as a fraction like this. So we don't want to round in any of these problems. We don't want to round this decimal. And so you're better off just leaving it as a fraction than rounding anywhere. Okay, so if you put that in as y1, that would give you that curve, and then we want to know when it reaches y2 equals 1500. That's the horizontal line, and they're showing that that intersected after 11.2 years. So same idea. Once you have the equations, you're just finding the intersection. Okay, so this is the formula you need when you're compounding any number of times per year. Even if it was 1 time per year, you can still use this, and would just be 1. And then notice that if you put in n equals 1, that equation turns out to be the same as the equation we used up here. If you put in n equals 1, then you get that same equation. Okay, so go to page 685, please, and try problem number 4. For this one, we're compounding daily, so what's n going to be? 365. Okay, go ahead and try that one. Okay, so for this one, we have the value of our account is going to be 8,000 times 1 plus 0.065 over 365. Raised to the 365t. Now here's where I was talking about not rounding the decimal. So if you type this part into your calculator to try to get a simpler expression, 1 plus 0.065 divided by 365. Here, I'll actually show it up here. So if you have 1 plus 0.065 divided by 365, it gives you that decimal. Now if you use part of that decimal and say you're just going to do 8,000 times 1.00018, for example, okay, you'll get close results, but they're not going to be very accurate. The larger t value that you put in, the more inaccurate your answer is going to be. So it's generally not a good idea to do any rounding. Just type it into your calculator just like that. So leave the 1 plus 0.065 over 365 in your calculator. And most of you, I saw when you got that, you graphed the value of your account and 20,000, and that intersected at 14.1 years. Okay, questions? All right, so how could you compound more than daily? Hourly, you could compound hourly, so you could figure out how many hours there are in a year. You could compound hourly. Okay, what would be more frequent than that? Every minute, every second. Okay, what would be more frequent than that? Every millisecond. Okay, and it would never end, right? You could keep. I could say I'm going to compound every half millisecond. Okay, and then so there's no limit to how often you can compound. So when we when we're compounding more frequently than that, conceptually the only word that we can use to describe that is compounding continuously. So compounding continuously means we're compounding every instant. Okay, so we're compounding every instant. And so when we compound continuously, this is the equation we use, V equals PE to the RT. So yesterday's lesson, we did a bunch of equations involving that magical number E, which is about 2.718. And I said we use E a lot because it does a great job of modeling exponential growth in nature, and here's an example in finance where the nice thing about using a base of E is that our growth rate is just part of the exponent. And so it's really easy to set up the problems that way. And so here you see an example, $5,000. So our the value of our account is starting at $5,000. And if we're compounding instantly, then we would just do E raised to the 0.035 t, and that's all you have to do. And so then that's going to compound every single instant. So more often than every half a millisecond. Okay, so that's the equation that models compounding continuously. And just as we've done before, if you wanted to know when that reached y equals 12,000, you would graph both, see where they intersect, just like we've done many times already in this section. Okay, so again, V equals PE to the RT. So that's principal times that natural number E raised to the RT. And I know there were some people that were actually typing in 2.718 every time they wanted to use E, but I want to make sure everyone knows there is an E button on your calculator. It's right, let me clear that out. It's right down here on the left side, E to the X. So that last red button I just pushed is, if you do second function, ln, that gives you E to the X, and then you can put whatever expression you want, E to the X or E to the 0.035x, anything you want to put in there. And so use the E button rather than typing in 2.718 whenever you're doing E. All right, so let's go to page 386. No, sorry, 686. Page 686. And try problem 5, compounding continuously. So you're going to use that new equation now, PE to the RT. Or some people just remember it as PERT. PE to the RT is PERT. So we have y equals 1550 e to the 0.04 t, and we'll call that y1, and y2 is equal to 2000. So when you put those both in the calculator, there it is, 1550 e to the 0.04x and 2000. When you graph that, you see the intersection, and then do second calc, intersect, first curve, enter, second curve, enter, and guess. Try to move a little closer, enter, and the intersection is at 6.37 years, so we'll call it about 6.4 years. Any questions on that one? Okay, the next section is on effective annual interest rates, and the book explains this a little bit differently than the way I do, so you're welcome to use the book's method if you want. They go through and explain the whole thing, but I think the reason why I use a different method is because I think it's simpler, and simpler is always better. And if you can do something without memorizing a new formula, then I'm all about that. So I'll show you that we get the same results. So what effective rate means is it's, you know, when you're compounding, let's say you are earning 5% compounded daily. That means by the end of the year, your account has actually grown by more than 5%. So how much more? And so that the actual rate that you get for the year is called the effective rate. And so that's what we want to do when we're comparing two accounts, is we want to find the effective rate, which is how much did you really earn, what percentage did you really earn for the year. And so instead of using this formula that the book uses, I try to make it simpler, and I say to find effective rate, which is also called annual yield. Just invest $1 for 1 year. Then subtract $1. Okay, and that'll give you your effective rate. Okay, so watch how simple this is. So in this first account earns 2.5% compounding quarterly. The second account earns 2.48%, but they compound more often. They compound monthly. So their rate's lower, but they compound more often. Is it often enough to make a difference? Let's compare. So account X, we're going to invest $1 for 1 year. So when we compound quarterly, so the value of the account after 1 year is going to be $1 is our principal. 1 plus 0.025 over, it's quarterly, so it's over 4, raised to the 4 times 1. So that's an expression I can just type right into the calculator. And so 1 plus 0.025 divided by 4 raised to the 4th power. This turns out to be 1.025235353. Okay, take that dollar off and you find your effective rate. Your effective rate is 0.025235353. Okay, so under effective rate, we can say that's 0.025255353. Okay, so that's for account X. Compare that to what they got. That's the same, isn't it? They just rounded to the they rounded to this decimal place right here, 0.0252. Actually, they got this one, 0.025235353. So if I round to this decimal place, that would become a 4, and that matches their answer. Okay, so did I write it wrong here? 52, oh, there we go, 3, 5, and that would round that to a 4. So that is the same as what they got. Okay, and then for account Y, again, invest $1 for 1 year. So there, that's going to be 0.0248 over, it's monthly, so 12 to the 12 times 1. If you put that in your calculator, parentheses 1 plus 0.0248 divided by 12, close the parentheses and raise it to the 12th power, you get 1.025083844. And if we round that, that is 0.02508. the same answer they got. So they just chop it off right there. And so just investing $1 for 1 year gives you the same answer that they get using their formula. So instead of memorizing a new formula, it might be easier for you to just remember $1 for 1 year. Okay? And so that's how you compare those two functions. And which one has a better effective rate? The first one. So even though they're only compounding quarterly, the rate is high enough that it's going to earn more interest by the end of the year than the one that compounds monthly. Okay, so in this case, compounding less often was better because their rate's a little bit higher. Okay, so that's how you compare them. All right, so let's go down to the next page and try problem 6. Compare these two accounts. Just add a third column on, or a third row onto your table where you're going to write the effective rate. All right, so if you're ready, you can take a look. And so for account X, I invested $1 for 1 year. And notice that our effective rate that we get, so we get basically after 1 year, you'd have 1.0424. And then when you subtract the dollar to get the effective rate, that's 0.0424. That's exactly the same as the rate started with. And that shouldn't be a surprise. We didn't really need to do all that work because this one, when we're compounding annually, that means we're going to get our effective rate. So when you compound annually, your nominal rate is the same as your effective rate. Okay? When you compound more often than once a year, that's where your effective rate will be higher than your nominal rate. And so for account Y, we put in $1 for a year at 365 compounds per year, and you get $1 and 4.26383 cents, and so our effective rate is 0.0427. If we round both of those to 4 decimal places, we have 0.0424 and 0.0427. So clearly, in this case, account Y has a higher effective rate, so that's going to give us more money by the end of the year. Okay, so account Y is better in this case. Any questions?